excited to share with you a little bit of my work. We're going to pull up the first slide now. Humans have always been consumed with high-level performance. But in the world of physical fitness, the pursuit of optimal performance has really been a growing global obsession for many decades. From speed, endurance, power, flexibility, coordination, balance. Specialized programs, practitioners, and equipment exist across all of these domains to optimize performance. This ranges from wellness to competition to healthcare. Now I'll just go without slides. All right, so what about the human brain? How about optimizing the performance of this? The core function of which most defines us as human, our cognition, our memory, our attention, our perception abilities. In that regard, we are tragically lacking. When it comes to optimizing the healthy brain, the main approach we have is education. And there, we have focused a lot more on transferring information content rather than improving how the core information processing systems of the brain function. How about the impaired brain when we have cognitive deficits? In that regard, the main approach we have has been really focused on this. Pharmaceuticals, trying to deliver an approach to improve the function of our brain really through the molecule approach. Now, I don't have anything that I feel inherently is wrong with the molecular approach to improving brain function. But when it comes to building a brain at the highest possible level, this approach really has not served us in the way that we most hoped it would. And so we need to have an approach that really is targeted, personalized, multimodal, and closed loop, acting across all of these domains. Let me tell you a little bit about what that means. We need an approach that's targeted, acting on the underlying information processing systems. And neither the educational approach or the pharmaceutical approach really addresses that. So let's talk about video games. As you know, the world of video games has been largely dominated as an entertainment form, right? And it has really extended across the domain of entertainment where people have felt for a long time that it's really just another manifestation of human mania, an enduring quality of going relentlessly after absolutely pointless goals. But we know that's not the case. We now know that video games have become a global obsession, right? We see that they're across all age groups, where the average age of a gamer is now approaching 40 years old. Both men and women play equally. And so we know that video games are a powerful influence of behavior. But can it be a way of changing our function of our brain? So what I want to do is talk to you about research from my laboratory, where we look at video games as a way of improving brain function, acting in a way that's targeted, personalized, multimodal, and closed loop. How do we do this? Well, we can think of it in this way. The fuel of this is neuroplasticity, the ability of our brain to change itself and modify in response to interactions with the environment. The mechanics that we use, we call adaptivity and feedback, and these create closed-loop systems in order to change how the brain operates. So how can video games act as a tool to improve our brain? This is basically what our approach is. What we're thinking about is that we can have an approach that's targeted, personalized, multimodal, and closed-loop using video games. How can this work? Well, the fuel of any engine is essential for it to move. In our case, it's neuroplasticity. Neuroplasticity means that our brain can remodel itself at every level, from structure to function to chemistry, all in response to an interaction with the environment. The mechanics of our engine rely on adaptivity and feedback. And I'm going to come up to this again in the next slide and explain in a little more detail. Video games act as a delivery system in order to deliver this medicine, this digital medicine to our brain. So let me break this down a little bit of what I mean, how this works. So you're playing a game. Something in your brain triggers a response. That response is a behavior. The game detects this behavior in real time, records how you're performing, modifies itself, and feeds back a new environment. It's this closed loop between between your brain and the computer that acts to improve the processing. The two main tools that we use are adaptivity and feedback. Adaptivity means that as you play the game can scale itself, its challenge to your ability in real time. And feedback lets you know how you're doing from moment to moment. We think that these are the critical tools that allow a game to change the brain in a powerful way. But we look at that only as the beginning, the sort of foundation that we move from there. We think that the video games act to activate networks, which gives it selectivity, but there are other approaches that we can add on top of it, neuromodulation and neurofeedback. How do we do that? In order to take neural data and use it in a closed loop, we have to capture it in real time. And in order to do that, we developed a new technology in our lab in collaboration with several other groups called the glass brain. So what you're looking at here is a combination of MRI technology with real-time EEG, which allows us to see the rhythms of the brain within a 0.2 of a second that they're being generated. We take all of this data, we bring it in, we use the MRI data to allow us to localize it, and what we have is this really powerful, beautiful way of traveling through a real-time brain recording while someone's interacting with the video game. So what this allows us to do is to now take that data and use that to guide the video game play. So let me break down to you our vision of how we see this working. So we go to the year 2015 where we are now. If you go to your doctor's office and you have a problem with your attention ability, you're likely to get one of these, as we described. What this is going to do is going to activate neurotransmitters receptors across your entire brain. This is a blunt instrument. It's not a powerful way to get a targeted effect, and because of that, we have to increase the doses to very high levels, and then we get side effects. And most of what physicians like myself do is really treat those side effects that are trying to be remedied by the medications that we're given. We hope that within 5 years, we can start reducing doses, decreasing the burden of these medications that do not have the selectivity, and then use a video game to selectively activate a circuit. We can then take EEG data with technology like the glass brain, feed that into the game algorithm, and then use that to drive the adaptivity and the feedback. So in essence, the video game would diagnose and assess weaknesses in how your brain is processing information, and then use that to guide the game algorithm. The other approach that we're working on is to take EEG data and feed that into a stimulator, like in this case, either direct current or alternating current stimulator, and then to use that to potentiate the circuit, so that the underlying rhythms can be potentiated by feeding in alternating currents. When we have all of this together, what we're looking at is an approach that's targeted to the underlying systems. It's personalized, not just to the individual, but how they change over time, in a way that our current educational or medical approach does not do. It's multimodal, acting across multiple systems at the same time, and what we have is multiple closed loops going at the same time. Just to redefine that, a closed loop is where we intervene in some way, we record the impact, and then we take that data, use it to modify our intervention, and create this closed loop cycle. This is exactly how our current education and medical system does not work. Right? You take a pill, you go home, months pass, and then you come back with your subjective complaints about your side effects or your benefits, and then a non-evidence-based decision is made. In this approach, we think that we can correct all of those deficits. All right, I'm going to give you an example of how this works right now from research that we've done in our lab. Around 8 years ago, I challenged my lab to say, can we create a customized video game to improve cognitive abilities in older adults who have deficits, using exactly the type of closed-loop approach that I just shared with you. And so, what we wanted to improve with these abilities, known as cognitive control abilities. What cognitive control is, it's our ability to interact with our complicated environment based on our goals. And we see this as being 3 parts. The first is attention, your ability to direct your resources on what's relevant to you and sustain it there. The second part is working memory. After that information is gone, how do you hold it in mind so that you could have your behavior manifested? And then the last part is goal management. What do you do when you have multiple tasks? These core cognitive abilities are critical for everything we do. All our higher cognitive actions that take place on top of these, our relationships, our safety, our work. Our careers all depend on these being a high level. We know that all of these skills decline as we get older, even independent of things like Alzheimer's disease. So my lab has been looking over the last decade for what are the neural signatures that underlie these, so then we can build a tool using video game support to improve them in older adults. So we have the hypothesis. If we put our game focus on one of these abilities, goal management, could we then lead to a benefit in attention and working memory abilities? And so in 2008, I had an idea for a video game. We call it NeuroRacer. And I reached out to friends of mine that worked at George Lucas's company in San Francisco, LucasArts. And I asked them if they would help build this game for us. This is a little bit of how the game looks. You're driving a car on a road. It takes a lot of attention using a joystick to keep your car there. And you have to respond as accurately and rapidly to these target signs. Green circles, but not red circles and not green pentagons, like you see here, which are the distractors. So what we have going on here are two tasks at the same time. Now these tasks are both competing for your attention. And what we do is we use independent adaptive algorithms for each of them. So what that means is that as you get better at driving tasks, the road goes faster. As you get better at the sign task, your ability to respond, your time window to respond gets shorter and shorter. So these tasks are competing for your attention at the same time. So what we're interested in is several things. First, can we use this video game as a diagnostic tool to look at multitasking abilities across the entire lifespan, from 20 years old all the way up to 80? Can we also use the game as a neural diagnostic to see what happens in your brain when you're multitasking? And then can we use the game in an adaptive mode to actually improve your attention and working memory abilities? So let's start. The first thing we find is that when 20-year-olds play this game and multitask, we see a 27% drop in performance. So a 0% means that you do the sign task as well when you do it alone, compared to when you do it at driving at the same time. And even though 20-year-olds feel like they're multitasking masters, that they will be perfect at this game, we see that they're not. They drop significantly in performance. But what happens across the lifespan? We already know that older adults are going to have a great challenge with this task. What we find is this. We find that this ability declines with every decade of life. So our ability to multitask is not something that gets worse once we're 60, 70, 80 years old. We even see a difference between 20 years old and 30 years old. The next thing we did is we had our older participants and younger participants were an EEG path. So we can look at what's happening in their brain during the most challenging part of gameplay, right when a sign comes up and you're driving the car. And what we're interested in here is something known as midbrain frontal theta, which is a burst of activity in a low frequency from the front part of the brain. Now if we take a look at 20-year-olds, we see this burst. You can see the yellow over there. So the nose is pointing up, the ears are to the side. This is a burst of activity within a third of a second after the sign comes up. And you can see in the legend there, yellow is around third way up the scale. Now if we look at the brain of a 70-year-old playing this game, what we find is this. There's a burst of activity, but it's only at the level of green, not even halfway up the scale. So what we show here is that we can use a video game both as a behavioral and a neurodiagnostic tool. What we do next is that we have our older adults take the game home, so here you can see playing it, and we do it for 12 hours of gameplay. So they play for 1 hour a day, 3 days a week for 4 weeks, and then we bring them back into the lab and we see what changes. And what we find is that after a month of play, we see that there's a drastic improvement in their ability to multitask, such that they exceed the level of 20-year-olds on a single gameplay. And you could also notice the real increase in activity from the frontal lobes. But what's perhaps most interesting is that first we see that this ability does not even decline 6 months later, despite the fact that they have not had a booster in the game. But what we also found was that our hypothesis was a reasonable one, that working memory, the ability to hold faces in mind for short periods of time, and their attention span also improved, even though these were not directly challenged in the gameplay. And that's the ideal thing that we're looking at. We're looking at this aspect of transfer. Can we see benefits and skills that were not directly challenged in the game? And we can see that. Now it's important to point out that there were two control groups here. A passive control group that did nothing, just look for practice effects, and then an active control group. that played NeuroRacer, but they played it in single tasking mode, meaning they only did the sign task or the drive task separately, but never at the same time. That group did not show an improvement in any of these abilities. They didn't show an improvement in their ability to multitask, and they showed no brain change. So what we start to learn is that these changes are selective to the multitasking environment of the game. The next thing that's important that we learn is that not everyone in our study, our older adults that train on this, shows this same degree of change. But those that show this change the most also show the most transfer of benefits to that other task, and they also show the most sustained benefits 6 months later. So we were pleased that this paper was published in Nature in September of 2013 after a 5-year study. So it was a year of game development and then 4 years of research. And what we show is that we can develop customized games, working with professionals in the video game industry, so that we build something that's immersive, engaging, and fun. And then do a careful, placebo-controlled study with neural metrics to show that we can get benefit in other abilities and understand what the neural mechanisms of that are. So if there is a game changer here, I'd like people not to focus on it being this particular game, but rather that methodology by which you can build a new intervention. What's happening now? First thing is that we are now doing these experiments. We're looking to see, can we use NeuroRacer and boost the effects by using glass brain technology to both drive the game engine during gameplay and to stimulate the brain during gameplay. So this is our vision of the future, that we can now enhance the effects that the video game is giving in itself to reach optimal levels of cognitive performance that we've never been able to obtain with our current approaches. What else is going on is that we're trying to move this technology out of the lab into the real world. One thing that we learned very well is that you can't build a scalable product inside an academic lab. So you need to work with industry in some ways. Here I helped co-found a company called the Killer Interactive Labs that's now building out a much higher level game, this is actually a tablet-based game, to see if they could create a product from this basic methodology that underlies NeuroRacer. The interesting thing here is that this game is not a consumer available game right now. It's going through multiple clinical trials, including an FDA pathway that's just about to start for ADHD, to ask the question, can a video game be a prescribable medicine? Can we take this game and reach all the same outcomes that we'd reach in a drug study, but with even a more favorable side effect profile? So all these studies from depression, traumatic brain injury, post-traumatic stress disorder, Alzheimer's disease, and autism have all begun now. So we'll know within the next couple of years how successful we are in that regard. In the meanwhile, now that NeuroRacer has left the lab, we're working to build new technology. We created this new lab at UCSF called the Neuroscape Lab to bridge high-tech, both software and hardware, with neuroscience to help yield education and health outcomes in a more powerful way. To give you a look at what our lab looks like, this is the building. It's only a couple years old, and this is our neuroscience lab. So not your typical lab, but I can assure you it's a neuroscience lab. So this is our experimental room where our participants engage in our interactive media, and then this is the control room, which is right across this wall. So while we create new media to challenge our participants, and they play it in this room, we record everything we possibly can, from their body movements to their eye movements to the heart rate variability to their skin conductance, including real-time EEG with the glass brain. So we have this back and forth across the room over here. I'm going to tell you a little bit about some of the technology that we're now developing here. The first is obviously we're very excited about wireless technology. Its accessibility to reach even across the world, even into the heart of Africa. We see cell phones are now present. It's going to take longer time, but hopefully we'll be able to get this technology in places where doctors and teachers might have a hard time finding themselves. We're not just interested in tablet-based, but we're also interested in devices, as well as this device here, which is a wireless EEG cap. And I know that there are other folks here that are building this type of technology. So over the course of this year, we're going to start to see how readily we can get the tools that we're building around the world, outside of the laboratory. Two other pieces of technology we're very excited about. Virtual reality, where we can create an immersive experience, and we think maybe even lead to higher levels of game improvement, and motion capture. to have people not just play games with their eyes and their fingers, but actually be physically embodied in the game. Let me just close the talk by telling you about 4 new games that we're building, now that you can see how we develop and how we test them. So the first game that we're very excited about is called Body Brain Trainer. The goal of Body Brain Trainer is to challenge our participants both physically and cognitively at the same time, so that we think that we can build the body and the brain together and reach a higher level. Here's a little bit of what it looks like. So here we use the Connect 2, part of the Xbox gaming platform. You play the game by doing these different cognitive challenges, but you don't just use your fingers, you respond with your entire body. Now you see that 159 up in the left-hand corner? That's our participant's heart rate. In addition to having the game adapted to your cognitive ability, our game adapts to your physiology. So we figure out what your ideal heart rate is using a VO2 max beforehand. And then we can hold your heart rate right at that level by adjusting the game dynamics. So until your heart rate reaches a level, you have to make larger, amplitude, quicker movements. Once you reach that level, we can titrate it back. So what we have is both physical and cognitive adaptivity working together. Our hypothesis is that the learning curve for attention and memory and the type of skills that I told you about will be greater if our participants are physically embodied in gameplay. So that's one of the games that's just going through testing now. And these are a quick view of what some of the other worlds. We built this entirely in our laboratory. The next game that we're excited about is a game called Rhythmicity. Rhythmicity, we work with many musicians to try to see if we can take the act of becoming more rhythmic and use that in our game engine to see if it can improve the rhythms of our brain. And so this is a work that's still several months away from being completed, but we think that the active ingredient that goes into musical training can be put into an algorithm, and then we can test it carefully in the lab. I won't go through that in detail. Our virtual reality game is known as Virtual Attention. This game is still in the design phase, but the idea is to take advantage of the wide depth of field, as well as the aspect of depth that exists in virtual reality, to teach people not just to focus their attention, but how to distribute their attention more broadly, the exact type of skill you use when driving. So this is now being developed in a very unique collaboration with Zynga, who's developing it philanthropically with us. And the last game I want to tell you about is a game that we call MetaTrain. MetaTrain takes the principles of concentrative meditation, and then we integrate it with our game mechanics of adaptivity and feedback to see if we can help people better self-regulate internal distraction. This is another game that we developed in collaboration with folks at Zynga. It's an iPad game, and this game is now also completed and has started to go through testing. So, in summary, we have 4 new games that have been developed in the lab. MetaTrain, Rhythmicity, Virtual Attention, and Body Brain Trainer. Our goal now is to see how they can act to improve the function of our brain. And so what we are now working on are multiple studies where we do MRI, EEG, stress testing, epigenetics, sleep monitoring before, during, and then after you go through the training of these games. Now, we don't think that the ultimate win is going to happen this year, that any of these games are going to lead to the real effects that we're looking for. Rather, we think that the interaction of these games, which we won't learn 2 years from now, is really going to lead to that, something that I call neuro-CrossFit training. So now, while all of this development is going on, it's going to take us a while to get to that point. I figure a little harmless self-experimentation is for me to engage in all these gameplay at the same time. Now, of course, we don't know what's going to happen with that, but I can tell you that I have very high-level expectations of what we'll find. So only the years will tell us, but sort of like a neuro Ironman I'm looking for. So I want to conclude with letting you know that there are multiple collaborations that we're now forming with physician scientists, both at UCSF and all over the world, to see if we can take these tools and have an impact across this large domain of clinical conditions that have an impact in cognitive abilities. And then our latest interest, which we're just starting this summer, is to see, can these games also serve as educational tools? can we move them into the classroom, use them as a way of assessing and optimizing brain function, even in young people who are healthy and don't have a clinical condition? And with that, I'd like to thank you for your attention.